On April 20th of 2023, Super Heavy Booster 7 savagely destroyed the blast surface under the Starship orbital launch mount. After 108 days of intense reconstruction work and making massive upgrades to the pad, SpaceX was back in action and performed a full static fire test with Booster 9. For the first time, we were finally able to see the new active flame deflector system tested against the immensely destructive forces of 33 Raptor engines. From what we can tell, the system seemed to hold up remarkably well. But the true test is yet to come. This 2.74 second reduced throttle test is only a fraction of what it will have to endure during the next launch attempt. But if it's successful, SpaceX will raise a finger in the face of everyone who said it was impossible to safely launch the world's most powerful rocket without a traditional flame trench. So while we wait for that day, let's explore the ins and outs of how the system is designed and get a better understanding of how all of this is intended to work. As I've said before, if you're looking for the How It's Made episode of Stage Zero 2.0, then you've come to the right place. My name is Zach Golden, and welcome to part 2 of this CSI Starbase Deep Dive Investigation. Hey everyone, thanks for joining us. In part 1 of this deep dive investigation, we explained the step-by-step process for constructing the upgraded foundation of the launch mount while working around the existing structure. If you haven't seen that episode, I recommend checking that out here first. Now that the Super Heavy Booster bidet system is mostly completed and operational, we can take an incredibly close look into how the system works. Throughout this discussion, you will hear me use various terms like booster bidet, shower head, pancake, or water-cooled steel plates. All of these names are referring to the same thing and are not meant to confuse you, but it helps me to switch it up and not say the same words over and over again. This deep dive is going to be much longer than part 1, so to help you out, I've created a list of topics that will be discussed here today. These will be broken up into the video timeline so you can easily jump ahead to different sections if you have to watch this over multiple sittings. I know that not everyone has the attention span for these long episodes, so I hope that helps. If you learned something new today, do us a favor and subscribe to the channel if you haven't already. Before we get started, I think it's super important that we explain what the actual purpose of this system is. Over the past few months, I've seen a lot of replies to my videos and comments on Twitter or Reddit that have made it pretty clear that there is still a lot of general misunderstanding when it comes to how this system is intended to work. So, I'm going to try to answer all of those questions here today. Let's start off with the most common question that I've received over the last year and a half. Why can't SpaceX use the same TPS tiles on the Starship to protect the blast surface and the 6 legs of the orbital launch mount? Some of you may think the answer to this is a no-brainer, which is why I haven't addressed it in the past. But when I say this is the most common question I receive, I mean anytime I put out an episode where we discuss the orbital launch mount, I get asked this question at least 20 times, if not more. Whoa, step very carefully. Okay, so to answer this question, we have to consider the fact that there are 2 different destructive mechanisms that need to be mitigated by this launch pad. The first is thermal energy. As you can imagine, there is an insane amount of heat produced by the 33 Raptor engines. Depending on where the measurement is taken, we could expect to see temperatures in excess of 2,000 degrees Celsius or 3,500 degrees Fahrenheit. And yeah, protecting flat or curved surfaces from extreme temperatures such as this is exactly what the Starship TPS tiles are designed for. As a spacecraft re-enters the Earth's atmosphere, it encounters increasingly dense air at incredibly high speeds, which causes a lot of friction. The friction between the vehicle and the surrounding air generates heat due to the conversion of kinetic energy into thermal energy. As an example, the surface temperatures on the space shuttle during re-entry were in the area of 1,477 degrees Celsius. This is fairly comparable to what we would expect under the orbital launch mount. So then, what's the problem? Well, next we need to consider the mechanical forces, which is something TPS tiles are not very well suited for dealing with. What I'm referring to is the force generated by the kinetic energy of the downward traveling exhaust plume being converted into pressure as it collides with the flat surface roughly 16 meters below the exit of the nozzles. Going a little deeper into the physics of this, the equation for kinetic energy is 1/2 mass times velocity squared. In this example, the actual mass of the exhaust flow is relatively low, but the velocity is very high. And when the high-velocity gases impinge on the flat surface, it wants to change directions rapidly, and that causes a buildup of pressure. It's tough to determine the exact value of stagnation pressure exerted on the ground, but we have estimated it to be somewhere around 17 bar. This is equivalent to 170 tons per square meter. For those who are wondering, we obtained these numbers by dividing the known thrust of a Raptor 2 engine by the area of the exit of the nozzle. It's important to note that due to the performance upgrades of Raptor 3, these numbers will be even greater in the future. So, how does this compare to the pressure that these tiles will experience during re-entry? Well, as the vehicle is traveling at high speeds through the Earth's atmosphere, it will experience some aerodynamic pressure due to the force exerted by the airflow on the surface of the vehicle. The equation for dynamic pressure is 1/2 times the density of air times the velocity squared. So if we take the value of the average air density at 60 kilometers above sea level, and assume the vehicle is traveling at somewhere around 27,000 kilometers per hour, or 7,824 meters per second, then you end up with a dynamic pressure of 0.1 bar. Now, compare that to 17 bar of stagnation pressure under the launch mount, and you can see that this is 170 times greater force being applied. TPS tiles just simply aren't designed for that kind of punishment. Seriously, these things have been known to break just by looking at them the wrong way. Look, case in point. Look at this. Anyways, hopefully that clears things up for those of you who have been asking this question. With that out of the way, let's analyze how this super heavy booster bidet will accomplish the job of mitigating each of the issues that we discussed. First of all, I want to be clear in stating that this system is not some kind of magical force field that shoots water into the exhaust plume in order to cancel out the thrust from the 33 Raptor engines. I think this idea is a result of an incredibly deep misunderstanding of a quote made by Elon Musk during his Twitter Space discussion following the integrated flight test. Let's go ahead and take a listen to it so we're all on the same page here.
Water pressure coming out of there has to exceed the pressure that the engine's thrust is exerting on the steel plate beneath the launch stand. So, which is all doable.
In this statement, Elon mentions that one of the critical design parameters of this system is for the pressure of the water as it's exiting the holes in the upside-down shower head to be greater than the stagnation pressure of the Raptor engines. The reason this is necessary is because if the pressure used to force the water out of the plates is less than the pressure created by the exhaust plume hitting the flat surface, then the water will not be pushed out of the holes, and instead the superheated exhaust plume will enter the plate. If this were to occur, it would likely result in an overpressure of the water system, which would be a pretty catastrophic failure. Luckily, there are safety features in place to prevent something like that from happening, which we will discuss later in the episode. Anyway, as long as the water pressure is greater than the stagnation pressure, there will be a steady flow of water out of the shower head. The most important thing to note here, as I said before, is that the flow of water will not cancel the downward momentum of the exhaust plume. In order to do that, the momentum of the water would need to be equal and opposite to the momentum of the overexpanded exhaust gases from the 33 Raptor engines. Because the water will be shooting out at a shallow angle and not directly into the plume, the change of direction of the exhaust gas won't occur until after it contacts the steel plate. At this point, the downward velocity of the plume will be 0, and it will want to change direction and begin moving outward. For the outer 20 engines, this isn't as much of an issue because the gases can easily exit from between the legs. But for the inner ring of 10 engines, and especially the 3 center engines, the gases will have a tendency to become trapped and could begin to recirculate. This recirculation further increases the pressure and temperature in the center of the blast surface. This is where the water jets come into play. As the water exits the nozzles of the plate, it will immediately transfer its outward momentum into the plume and encourage it to move sideways, away from the center of the table. A portion of this water will be instantly vaporized, resulting in an increase in pressure, which could further assist with forcing the plume outwards. While this is occurring, the remaining water will be driven down to the surface of the plate. At this point, the water and steam should form an insulating layer on top of the plates. While the top surface of the shower head will still become very hot, the water will absorb a large amount of the thermal energy. This is what prevents the steel from melting or being quickly eroded away by the largest cutting torch in the world. One concern that a lot of folks have expressed is the possibility of the steel becoming hot enough to begin boiling the water while it's still inside the plates. If steam is being generated inside the plates, the resulting pressure increase theoretically could result in a steam explosion under the right conditions. Now, I don't think something like this is even really possible due to the fact that the steam should easily be able to escape out of the thousands of small holes in the plate. However, for the sake of being as thorough as possible, I asked Andy, who is the creator of the Starbase Sim video game, to put together this simulation which shows the heat transfer through a 1.5-inch or 3.8 centimeter steel plate with a heat load of 10 megawatts per square meter. Stainless steel has a melting temperature somewhere between 1,400 and 1,530 degrees Celsius. Without giving consideration to the cooling effect of the water and steam, we can see that by the time the backside of the steel plate reaches a temperature where it could begin to boil the water, the steel on the top side of the plate will already be well beyond its melting point. This means erosion of the top surface will already be occurring, so we shouldn't really need to worry about any steam explosions inside of the shower head. It's also worth mentioning that an added benefit of the water is that it should also absorb some of the acoustic energy. Unfortunately, we don't know how this will compare to a more traditional water deluge system, so we can't really say much on that subject. While this explanation is far from perfect, hopefully we can all agree that the water is mainly responsible for absorbing thermal energy and assisting in the change of direction of the exhaust plume. It's important to understand that the stagnation pressure acting on the blast surface will not be canceled out by the water jets. Even if it was, the pressure of the water as it's exiting the nozzles would still be exerting a downward force on the plates, which would be equivalent to or greater than the net engine force. With that said, it's inevitable that these extreme forces will need to be transferred through the steel plates and into the foundation. For this reason, it's extremely important for the foundation to be strong enough to handle these forces without cracking under pressure like it did during the integrated flight test. In my opinion, had Booster 7 not completely obliterated the blast surface and created a 4-meter deep hole in the ground, there is a strong possibility that SpaceX would have installed the system without adding any additional reinforcement to the foundation. So, to some degree, minus the impact to the surrounding environment, it's probably a good thing that this happened, because as a result, it gave them the critical data they needed to prevent a more costly failure from occurring in the future. The 3-month downtime that we saw here is nothing compared to what it would be if they destroyed the system and had to rebuild a new one from scratch. I would expect to see these same changes made to the foundation of the second launch mount at Pad 39A. As mentioned in previous episodes, SpaceX has already installed the water manifold system for this launch pad back in December. But as far as I can tell from the limited coverage we have of that launch facility, the foundation seems to have been constructed very similarly to the original structure at Starbase. Thankfully, the launch mount has not been installed at that location yet due to a halt on construction that took place at the beginning of the year. This should make it easier for them to perform the necessary upgrades. Anyway, there was a ton of additional work on the foundation that occurred after Part 1, which I could probably spend a half hour talking about. Instead, I'm going to try and summarize it quickly so that we can move on to the more exciting stuff. I considered skipping this altogether, but I think it's very important information considering this is the part that Elon referred to as overkill. So when we left off, SpaceX was preparing to pour the second level of the foundation under the launch mount. If you saw that episode, then you will remember that the bottom layer was roughly 1.8 meters thick, while the upper layer was 2.2 meters thick. Both of these layers were heavily reinforced and were also tied into the exposed rebar from the original hexagonal tension band. Tying the 6 legs of the launch mount into the rest of the foundation provides several benefits. First, the weight of a fully loaded Starship and booster are no longer supported exclusively by the 6 pilings for the legs, but it will also be shared by the 9 pilings in the center and the 15 pilings located on the outer perimeter. More importantly though, the load from the stagnation pressure will be distributed across all 30 of these pilings. Don't forget, not only is there roughly 17 bar of pressure in the center of the table, but there will also be a pressure gradient extending several meters beyond the radius of the legs of the launch mount. As if this wasn't enough, before the top layer of concrete was set, SpaceX also began laying rebar for the outer perimeter of the pad. As you can see in this image, all of this was tied into the foundation as well. It's also supported by 11 of the smaller CFA pilings placed outside of the main load-bearing foundation. As a result of all these sections being structurally tied into the foundation, it makes it significantly less likely, if not impossible, for the booster to lift away sections of concrete in these areas like it did last time. The only reason this occurred before is because the different sections of concrete slabs in these areas were all poured separately from each other and none of them had rebar in between the sections to structurally tie them together. That is very evident when you look at these images of the aftermath. After the first half of the pad was laid, you can see that there was rebar extending beyond the edges to allow the southern side to be physically tied into the northern side. There was also rebar extending out of the first layer of concrete, allowing it to be tied into the secondary layer. Due to the presence of the water manifolds, they would be unable to physically connect everything to the top layer of the foundation on this side. So instead, you can see that in this image from Starship Gazer, they installed Nelson studs on the rear cover of the water manifold with additional studs on the sides as well. They also took this one step further and added them to the bottom of the steel flame diverters on the legs of the orbital launch mount. You can see what this looks like once the rebar is in place before the final pour. Calling it the final pour is a bit misleading, however, because there was still one more step after this. Returning to the aerial view, when we look at the northern side of the pad, You can see that after this high-strength concrete was laid, there was still a final layer that would be used to create a sloped ramp up to the steel plates in the center. Also visible here are exposed rebar extending upward from the layer underneath, as well as from the outer edges, which makes it so, once again, everything is tied together.
Sorry for the extreme amount of repetition, but I really want the importance of this concept to sink in.
The final touch on this job is perhaps my favorite part of this whole thing. Over a period of about 2 weeks, 190 bags of Fondag RS were delivered to the launch site. Yes, this is the same heavy-duty extreme heat-resistant concrete that was used under the launch mount prior to the first integrated flight test. In that situation, there was about 12 bags worth of Fondag used to create the blast surface, so this is nearly 16 times that amount. After being mixed on site, it was lifted into place one bucket load at a time instead of using a pumper truck. This is likely due to the steel fibers embedded within the aggregate mixture. Not only did they use this to form the ramp that I mentioned a few minutes ago, but we believe it was also used to fill in the gaps between the shower head and the wedge-shaped flame diverters on the legs of the launch mount.
Some of you may be wondering, why would SpaceX use this again if it failed the first time? Well, first of all, the Fondag didn't cause the failure, it was the concrete layer underneath that gave way. Second, in my opinion, the application that it was previously being used in is not what it's designed for. Fondag is best used on indirect blast surfaces that aren't exposed to direct fire from supersonic cutting torches. When placed outside of the direct blast zone, it won't experience the same kind of erosion that it would under the launch mount. This is probably the best possible way of protecting the concrete outside of the steel plates from thermal shock, other than constructing a flame trench. When all is said and done, I think it's nearly impossible for this foundation to fail again like it did on April 20th. But we will soon find out. So now that we have a good understanding of the serious upgrades to the foundation of the launch mount, let's take a look at the actual water-cooled steel plates. First, we will begin with the most important component of the system, which is the massive steel pancake. This is essentially the centerpiece of this entire system. When we left off on part 1 of this deep dive, SpaceX was in the process of rolling out this massive structure, and we had a few unanswered questions, which we believe we now have a much better understanding of.
One of the biggest questions that we had was related to the threaded holes located on 3 out of 6 sides of the pancake. These are oriented on the north side of the launch mount, where there are no pipe manifolds supplying water to the shower head. From what we can tell, making these internal threads was one of the most time-consuming parts of this fabrication process. These are some pretty massive holes, and in order to tap them, it required several workers to take turns jumping off of ladders or the top of the plate while holding the extended leverage bar. Not gonna lie, this footage from Starship Gazer was pretty entertaining to watch. I've linked it in the description if you would like to check it out for yourself. After the holes were finished being tapped, threaded end caps were inserted into the holes. There are 10 of these on each of the 3 sides where they are present. It took us a while to figure out the purpose of these holes, and it didn't become clear until the entire system was finished being installed, so we will come back to this here in a few minutes. Moving on, once it was time to install the pancake, the process was pretty much identical to the animation that we showed in part 1 of this investigation. After it was in place, it was actually lifted up several times and placed back on top of pipe stands. We believe this was done in order to allow them to shave down the embed plates to make sure they're perfectly flat against the bottom surface of the pancake. Around this time, an interesting photo showing the plate as it was being lifted was posted to Twitter and later deleted. One of the details that stuck out here was the fact that the concrete was not poured all the way up to the top level of the embed plates. As you can see here, there was a 1 or 2 inch difference between the concrete and the top of the embed plates, which I thought was pretty odd because it would allow the plate to sag in the center, albeit not by very much. It turns out that this was done intentionally so that the final layer of concrete could be poured just before the plate was set down for the final time. In this footage from NASA spaceflight, you can see the mixer truck pull in and deposit the final load. A few minutes later, the plate was lowered into position while it was still wet. By doing this, they were able to perfectly fill the gap without having any unexpected high or low points. After this, they were finally able to begin permanently attaching the plates to the foundation by welding them on the outer edges. The next step was to install the water manifold sections. There are 3 separate manifold sections, and each of them are different in design. On the side furthest from the integration tower is where the largest of the 3 manifolds was positioned. This 5-foot diameter manifold has 18 pipes arranged in 2 rows of 9 that feed into the steel plate section. There is another pipe branching off of the bottom, which we unfortunately never discovered the purpose for. On the inside of the plates, there are 18 vertical channels and 1 pipe for each channel. Next up is the medium manifold, which was installed on the southern side of the launch mount. This 4-foot diameter manifold has 26 pipes feeding into the steel plates.
These had to be arranged in 3 separate rows in order to make them all fit. As you can tell, this manifold appears to be designed to have a much higher flow rate of water. On the inside, there are still 18 channels, but as you can see, some of them have 2 pipes feeding into the plate. Finally, there is the small manifold located on the side closest to the integration tower. This 3-foot diameter manifold had to be constructed differently to allow it to fit next to the concrete culvert containing all of the GSE pipework for the integration tower. This section has 16 pipes feeding into it, with all of them attached to the back side of the plate since there wasn't enough room to attach them to the bottom. There are still 18 channels in this section, so the 2 that are on the end are left without a supply pipe. Once all of these were in place, the next step was to install all of the pipework. We aren't going to go too much into detail into this other than to say that the large and small manifold are joined together via this reinforced Y-pipe section that has a 5-foot supply pipe. This pipe is connected to the group of 4 smaller water tanks behind the integration tower. The medium manifold in the center has its own 4-foot supply pipe which is connected to the 2 larger water tanks. Later on in the episode, we will discover why this 2-stage system is necessary. The final thing to mention is that in the culvert box where the 4 and 5-foot pipes connect to the underground pipe sections, there is a T-section with a cap placed on top of it. Inside of this cap is an adapter that allows sensors to be placed inside of the pipe. This is more than likely for monitoring the pressure downstream of the water tanks. After each of the manifold sections were in place, they were welded to the embed plates around the edges just like the shower head. There was a small gap on the leading edge of the top plate, which allows them to join the bottom plates together with the centerpiece. Not only are they welded to each other, but they're also simultaneously welded to the embed plate below. Next, the vertical supports are installed before adding a strip of steel to close the gap. After this, the rectangular end caps on the opposite side of the pancake, which do not have water manifolds supplying them, were lifted into position. This is where the threaded holes come back into play. Initially, we believed that the purpose of these holes was to allow SpaceX to modulate the amount of water flowing into the rectangular end pieces. If they tested the system and realized that they wanted more water flowing through these outer plates, they could remove some of the caps from these holes until the desired flow rate was achieved. But as it turns out, these rectangular sections are not designed to have water flowing through them at all. So with that said, the only reason for having large holes in these locations is for the purpose of cleaning out the inside of the shower head. By removing the caps, they can flood the system and allow large debris collected on the bottom of the plates to be drained out of these locations. Without this, the only way to clean out the system would be to force the water out of the perforations in the top plate under high pressure. As you might be able to imagine, that is not very ideal, mostly because you can't control where it's going if you do this. Once all of these steps were completed, the final touch was to cover up the gaps between the shower head and the wedge-shaped flame diverters. Even though there was already fondag in these areas, it appears that SpaceX wanted everything within the footprint of the launch mount to be covered in steel. After this, angled plates were welded to the bottom of the wedge-shaped leg shielding and the outer edge of the pancake. The slope of these plates creates a wider angle for the water and exhaust plume to flow past and should help prevent the bottom of the legs from being eroded. In my opinion, the final product is amazingly well done, and it's crazy how fast all of this work was completed.
All right, it's time to turn our attention to the water storage tanks. Another question that a lot of folks have been wondering is how does the volume of water used in this system compare to a typical water deluge system like the one at Pad 39B, where NASA's SLS rocket is launched from?
Well, unlike the gravity-fed deluge system used at most launch sites, the water used in this flame diverter is stored in 2 groups of horizontal tanks. It's hard to get precise volumes on these, but by performing a little pixel math with overhead images from RGB aerial photography, we were able to come up with a reasonable estimation for the volume in these tanks. Starting off with the group of 4 short tanks, each of these vessels has a volume of roughly 116,000 liters, which is equivalent to about 31,000 gallons. The combined volume of these tanks is nearly 466,000 liters, or 123,000 gallons. Moving over to the larger water tanks, each of these can hold 310,000 liters, or 82,000 gallons. Once the third tank is installed, the total will be 933,000 liters, or 246,000 gallons. As you can tell, the volume of the 3 larger tanks is almost exactly double the volume that is stored in the group of 4 smaller tanks. When we look at the total volume of all 7 tanks, we end up with about 1.4 million liters, or nearly 370,000 gallons. From what we were able to determine, this is about 82% of the capacity of the water tower used on NASA's SLS water deluge system, which holds an estimated 450,000 gallons. With that information out of the way, the next question is, how is SpaceX filling these water tanks? If we look at the area in front of the storage tanks, you will notice a small pipe manifold with 4 individual fill ports. This allows for up to 4 water trucks to be offloaded simultaneously. Once the water enters the manifold, there is a hose that runs over to a boost pump, which then sends the water into the top of the first large water tank and the 4th small tank. There is a large 4-foot pipe manifold connecting the large water tanks together, and a 5-foot manifold for the group of smaller tanks. We have not been able to locate any valves on these water manifolds, which means that the water level will be the same at all times in each group of tanks. Thanks to this animation from Benedict 3D, we can see that because there are no valves on the bottom of these tanks, the first thing to be filled with water will be the 2 manifolds that connect the tanks together within their respective groups. After the manifold is flooded, the water will finally begin filling the actual water tanks. It's important to note that the water level inside of the tanks will be equal to the height of the water inside of the weir pipe. As you may expect, this will only fill one side of the weir pipe. Before using this system for the first time, SpaceX also needed to flood the long stretch of 4 and 5-foot pipes that run between the weir and the launch mount. Instead of using the gas pressure to force water over the apex of the weir, there is a small pipe that branches off of the 5-foot manifold in this location. From here, it splits into 2 separate valves, which are then routed to the other side of the weir pipe. These are essentially what we would consider to be prime-up lines. Opening these prime-up lines allows SpaceX to flood the pipes all the way up to the launch mount. As long as the level of water within the group of 4 smaller tanks is higher than the top of the pancake, water will begin to bleed out of the holes, as you can see in this footage from NASA spaceflight.
As far as we can tell, once this side of the system is fully primed, there doesn't appear to be a way of draining the pipes again. But in reality, there shouldn't really be any reason to do so. This side of the system should remain flooded at all times. If not, priming up the system would subtract away from the water in the tanks, which would require them to be topped off again. These 4 and 5-foot pipes hold a pretty large volume of water. Speaking of topping off the tanks, it's time to answer another big question that a lot of folks have been wondering. What kind of water is being used in the system and where is it coming from?
As of now, we have been able to confirm at least 2 locations where the water tanks are sourcing from. The first is located inside of the Sanchez site. In this footage from LabPadre's Raptor Boost camera, we can see 2 trucks filling up at the backside of the property near the Starship SN2 test tank. Looking at this from the aerial view, we can see that there is a water treatment facility that has been located here since February of 2022. This is a multi-stage treatment facility which pulls groundwater from this well and converts it into what would be considered potable water. There is another water purification site located within the Massey's test site, which I believe is another source that SpaceX is pulling from. However, we have not been able to confirm this. The second confirmed water source is located within a neighborhood in Brownsville. Shout out to Jack Beyer from the NSF team for tracking this down. Just like the 2 water treatment facilities at Starbase, this should also be a potable water source.
All 3 of these sources are treated to levels that should meet state and federal standards for consumption. So they are very clean water sources. All right, now let's discuss the high-pressure gas system, which is used to force the water out of the storage tanks. For the most part, this is a relatively simple system, but there are a few very important design considerations that have to be addressed. A lot of this stuff is currently hidden behind scaffolding, so we're going to use this amazing render from Benedict 3D to explain this part.
When we look at the storage tanks, you will notice that each rack of tanks has 2 vertical manifolds, which split the racks into 2 halves. Between the 4 vertical manifolds, there are 76 branches, or header pipes, connecting to each of the individual tanks. From there, the small manifolds combine into a single pipe laying on the ground in front of the tanks. It's important to note that there are no valves present in this manifold up to this point. This means that all 76 tanks are open at the same time, and the pressure is equally shared among them. The first valves in this system are in this location, which I will consider to be the primary distribution manifold. The number of valves that are in the open position controls the flow rate of gas that is available to be split between the 2 groups of water tanks. After this, we have the secondary distribution manifold, which controls how much of the gas is delivered to each set of tanks. On the left side, there are 6 blue valve actuators which manage the flow to the group of 4 smaller tanks. On the right side, there are 6 red valve actuators for the larger group of tanks. It's important to note that not only are the valves larger, but so are the header pipes on both sides of the valve. The pipe that is used to send the gas to the top of the water tanks is larger as well, to allow a higher volume of gas to be sent to these tanks, which, as we mentioned, hold twice the volume of the smaller group. It's important for the control system responsible for actuating these valves to balance the pressure within the water tanks to make sure that they don't overstress them beyond their maximum rated pressure. On top of each of the tanks are a set of sensors which monitor the water level and internal tank pressure. These values are likely reported back to a control system which regulates the flow of gas to the tanks. Theoretically, this kind of control system could also allow them to automatically adjust the flow rate of gas based on changes to the thrust output from the booster's engines. To protect the water tanks from a possible overpressure, there are burst discs installed in these 4 locations. These are mechanical burst discs which will rupture once the pressure exceeds a certain value. Ideally, you don't want this to ever happen. If it does, it would probably be critical for the booster to immediately shut down its engines in order to prevent damage to the shower head and water storage tanks. As you may have noticed, SpaceX is in the process of installing 65 additional high-pressure gas tanks adjacent to the original group of 76. I believe the reason for the extra tanks is partially related to the fact that there will soon be another large water tank added in this area. This should also future-proof the design to make sure that when Booster 10 or 11 begins to use the upgraded Raptor 3s with higher thrust output, they're able to increase the output from the showerhead as needed.
The question that we've been trying to figure out for the longest time is, where is the high-pressure nitrogen needed to fill these gas canisters coming from? Well, we believe we finally have a solid answer for this. Those of you who watched my most recent episode will remember that I was looking for an ambient air vaporizer to be located somewhere near the water storage tanks. A few days after that episode, SpaceX installed this vertical storage tank along with an ambient air vaporizer just as I was looking for. At first, I thought this was an aha moment. However, it's pretty clear that this pressurization system was already active before these were in place. And considering they don't appear to be fully hooked up yet, we don't think it's related to the system at all.
Just for confirmation, thanks to this picture from Starship Gazer, we can see a label on one of the new control panels, which shows that this is actually part of a CO2 tank farm storage system. As I said, this is completely unrelated to the deluge system, so I'm not going to address its purpose here today. So the real source of nitrogen, as it turns out, happens to be located inside of the orbital tank farm. Interestingly enough, this was actually the very first component of this system, which was installed back in December of 2022, 5 months before the integrated flight test. What you are seeing here is a forced draft ambient air vaporizer, which was mounted on top of a frame with a fan underneath it. On top of the fan is a radiator box, which has several small pipes connected to one end. We are assuming this is a hot water radiator box. This is different from nearly every other vaporizer on site, and as far as we can tell, it's the only one that makes use of a fan to force hot air across the finned tubes in order to accelerate the heat transfer process. Located next to this vaporizer are 2 sets of cryogenic piston pumps, which are used to send high-pressure liquid nitrogen into the vaporizer. By forcing the liquid nitrogen in at high pressure, it makes it so that the resultant gaseous nitrogen is also at a significantly higher pressure than it would be otherwise. After getting a good look at some of the pipe labeling on the fan assembly, we were able to determine that the output gas pressure from this system should be around 400 bar. This aligns with what we were expecting the pressure of the nitrogen within the gas cylinders to be. We haven't been able to determine how this line reaches the integration tower, but at the beginning of June, we noticed 2 small pipes freshly mounted on the wall near the doorway on the south side of the structure. These pipes appear to be routed underground and re-emerge near the base of the 4-foot diameter weir pipe. For reasons we are unsure of, the pipes are mounted onto the side of the weir pipe instead of taking the shorter path through the concrete culvert located nearby. From there, it travels underneath the water tanks and then connects to the distribution manifold for the high-pressure gas tanks. As I said before, this has been one of the most difficult parts of this system for us to figure out, but we're fairly confident in our conclusions due to the fact that we have observed activity from this vaporizer shortly before each of the flame deflector testing events that have taken place so far.
Based on a lot of the comments to my previous episode, I'm sure that some of you are still wondering why SpaceX couldn't just use compressed air instead of nitrogen. Well, the reason is because a system like that is slightly more complex and probably requires a lot more maintenance. If compressed air is used in a system like this, then you have to worry about contaminants in the air. There are 3 contaminants that are of concern here. The first is general dirt from the environment. The last thing you want is dirt being collected inside of the high-pressure gas tanks or making its way into the water tanks. A simple air filter could be enough to prevent this from happening, but that would require regular changeout of the filters, which would probably become dirty again rather quickly in this environment. The next contaminant is moisture. When storing high-pressure gas inside of tanks like this, it's important to keep moisture from building up inside of the tanks. The reason for this is because of the possibility of organic materials being contained within the water, which would then begin to grow inside of both the high-pressure gas tanks and the actual water tanks, especially if they're sitting unutilized for long periods of time. These organic materials also happen to be the third contaminant. This would require 2 separate filters to remove moisture out of the air and another to remove all organic materials as well. As with the particulate filter, this requires more maintenance to keep those systems running optimally. With that said, I think it's much simpler for SpaceX to use a nitrogen-based system. All right,
Now that we have all of this background info out of the way, let's get to the fun part. The first test of this system occurred on July 17th. By now, most of you have already seen this footage, but today we're going to look at it from a new perspective and get a much better understanding of how this pancake is designed. One of the first important observations that we were able to make occurred 1 hour before the start of the test. This is when SpaceX began slowly bleeding water into the showerhead. As you can see in this footage from NASA's spaceflight, the water was visibly flowing over the edges of the end caps. The most likely method for achieving this slow flow rate would be to use the prime-up lines that we mentioned a few minutes ago. We believe the purpose of this was to slowly begin flushing the inside of the plates to remove as much of the leftover construction debris as possible. In order to do this properly, they would have likely removed some or most of the threaded caps on the 3 sides of the showerhead that didn't have water manifolds connected to them. With this first step completed, it was time to run a partial test of the system. As we watch this, we're going to pay close attention to where the water is being ejected from. Thanks to this slowed down footage from Starship Gazer, once the system is activated, we can see the water spraying out from 3 separate locations. The first area where the water appears to be ejected from is on the far side of the central hexagon. This corresponds to the outer plate, which is connected to the medium-sized manifold. As a reminder, this manifold is connected to the 4-foot diameter pipe and the 2 larger water tanks. Next, we see another layer of water rising out of the central hexagon. A few frames later, you can see a third layer rising up in front of the centerpiece. If you pay close attention here, you can actually see what appears to be 8 to 10 individual streams combining together and then splashing up out of the plates, almost as if it just ran into a wall or something. When we look at this footage from NSF, you will notice that this does not happen on the left side of the screen, between the other set of legs where there is another rectangular end cap. Unfortunately, we can't see what's happening on the far side where the third end cap is positioned. Finally, let's take a look at one more angle from the other side, where you can see that the water coming out from the left side of the launch mount is shooting significantly higher into the air than it is anywhere else. That zone we are viewing is the location where the medium manifold is located. So, what does this tell us about the internal design of the showerhead that we didn't understand previously? Well, the first thing this tells us is that we had the internal design of this structure completely wrong. Initially, we believed that the vertical supports on the inside of the plates looked something like this. In this design, Ryan assumed that the central hexagon had holes on all 6 sides, which would allow water from all 3 supply manifolds to spread throughout the entire showerhead. But, based on what we are seeing, this simply isn't possible. Instead, thanks to this footage, we're able to determine that the medium manifold is the only one directly supplying water to the central hexagon. This means that the large manifold to the left and the smallest manifold on the right are supplying these 5 zones here. But this doesn't explain the small splash of water that we viewed on this side of the plate. Because of this, we realized that there must actually be a few holes on this side of the hexagon, which is allowing for water to reach the far side of the showerhead and exit out of the threaded cleanout ports. The reason there is a delay between the 3 different layers of water is because with these threaded caps removed, the showerhead would have been partially empty at the start of the test. As the system is activated, the outer plate for the medium manifold would fill first, followed by the central hexagon. After this, water would begin filling the outer plates and finally begin spraying out of the open holes. After the water leaves these holes, it would impact the 16-inch high wall on the end cap and then spray directly upwards. The reason it's necessary to have holes on this side is because without them, there would be no way of draining and cleaning out the central hexagon area. A secondary purpose of this is to allow the pressure to equalize between the different zones. As you can tell, a lot of careful thought went into the design of this system. After this test was concluded, SpaceX workers returned to the pad and immediately began some additional cleanup work that I think is important that we don't overlook. A few minutes ago, I mentioned the construction debris inside of the plates needing to be flushed out. This should mainly consist of metal shavings from all of the welding and subsequent grinding that took place in the days prior. As you can see in this footage, SpaceX made sure to take care of anything that may have drained off of the side of the pad. Most of this debris would have come out during the hour-long flushing of the system before the test occurred. Most of the water that we observed during that period would have ended up contained inside of this area where they had yet to lay the final layer of fondag. From there, it drained off the side of the pad and into the dirt behind the black silt fence. At the end of the test, a much larger amount of the runoff was also visible in this area, which would have carried away a lot of the remaining debris. Because of this, SpaceX removed all of the potentially contaminated dirt and transported it away from the site. Later, they went back and placed new dirt in that location before conducting the full pressure test the following week. We also observed them doing this on the opposite side of the launch mount, where they had not yet completed the concrete work. Okay, so moving forward, it's time to take a look at the full pressure test of this system, which took place 11 days later on July 28th. Let's see what we can learn from this. As expected, the full pressure test looked much different than the initial system test. And not just because of the fact that all 3 manifolds were tested instead of only the medium manifold. Looking at this footage from Lab Padre's Nerdo camera, we can see that as soon as the gas begins flowing into the water tanks, valves on top of the weir pipes are opened. The moment the valves are opened, you can see a geyser shoot straight up into the air. For some reason, this did not occur during the partial test, which is why I didn't mention it earlier. As you can see in this animation from Ryan Hansen Space, the purpose of this is to bleed all of the air out through the apex of the weir until the air bubble inside is gone. The flow of water over the weir is relatively violent as a result of how quickly the water is being forced out of the tanks. This causes it to begin spraying out of the open valve almost immediately. We aren't sure if there's a sensor that tells the valves when to close, or if they're simply left open for a set amount of time. Either way, this process takes about 4 seconds, and once the air bubble is purged from the system, the valves slam shut, resulting in a noticeable increase in the hydraulic pressure of the water being ejected out of the holes in the plate. At this point, we can consider the system to be at its maximum flow rate. In my opinion, this is likely the moment where the booster's 33 Raptor engines will begin their ignition sequence, but it's possible it will happen a second or two after the valve closes. This period of maximum flow rate lasts for approximately 8 seconds. After this, the bleed valve on top of the 5-foot weir pipe for the smaller set of tanks finally opens back up. The depress valves on top of the water tanks are also opened at the same time. 3 seconds after this, we see a bleed valve on the 4-foot weir pipe section open as well. Almost immediately, we can notice a drop in the volumetric flow rate of water spraying out of the shower head. Over the next 50 seconds, we can see the pressure within the system slowly bleed off until it finally comes to an end. Just for fun, let's try syncing up the timing of this footage with the video from the integrated flight test. For this, we're going to align the moment of ignition with the instant that the bleed valves close on top of the weir pipes. Once we do this, you can see that as soon as the booster throttles up and begins to lift off of the pad is the moment where the maximum flow rate period comes to an end. Since we are expecting the startup sequence to be much faster next time around, I've increased the speed of this footage by 25%. Alright, now that we can see how the timing of all these different events line up, let's look at the incredible view from above which was shared by SpaceX. I'm really grateful that they provided this angle from the drone camera because it allows us to see some details that we would otherwise not have noticed. One of the biggest observations when we look at this footage is that the placement of holes along the outer plates is a lot different than we were expecting. Initially, we believed that each of these dark spots represented the location of one of the perforations through the shower head. This would have essentially created evenly distributed rows of holes across the plates. But, as you may have noticed already if you've seen this footage, the water jets are actually concentrated in the positions where the outer 20 Raptor engines are located. Outside of the radius of the outer 20 engines, there are additional jets located in front of the flame deflectors on the 6 legs of the launch mount. This is obviously to protect the legs from the intense heat. As far as we can tell, there is no water being ejected in these areas, which was extremely confusing given that there appear to be markings where additional holes are located. We believe that the reason for this is because the process of cutting the holes into the plates likely took place before the plates were even assembled. The most likely method of cutting these holes is to use a 5-axis water jet, which was probably one of the very first steps in the fabrication process. It's possible that SpaceX wasn't sure how they wanted the final design to look as far as hole placement goes. So, to be safe, they cut way more holes into the plates than would end up being used. Once they settled on the final design, we believe they welded all of the extra holes shut. After welding them closed, they would have used a wheel grinder to smooth out the top of the welds. Looking back at this image from when the plates were installed, you can see what I'm talking about. These areas are holes that have been filled in. Anyway, back to the overhead shot, I should also mention that there appears to be a large concentration of water jets in the positions where the inner ring of 10 engines are located. In the center of the plate is where the highest concentration of holes are found. Essentially, this is designed to be the area where the greatest volume of water will be exiting from. The water jets in this zone are angled at roughly 30 degrees, which causes the flow to intersect with the spray coming from the other 30 engine positions. The primary purpose of having a higher volume in this area is to help the change of momentum of the exhaust plume and force it outwards. This is extremely important and is the reason there will be nearly 2 times more water spraying from the center than there is from the outer zones. As you may have noticed, there is a very small area in the center where it appears there was no water flowing out of. This has led some folks to assume that this will be some sort of weak spot in the flame diverter. But it's important to note that due to the position of the 3 center engines, there will not be an exhaust plume acting directly on the center point. At this distance, there will not be enough outward expansion of the flames from the 3 center engines to cause it to form a combined plume. Therefore, I think there's really nothing to worry about. The final observation I want to point out from this footage is the arrangement of small pipes that you can see in various locations across the top of the plate. These are most likely pressure sensors of some kind, which have been inserted into some of the perforations. There are 8 of these sensors in total, one for each of the 6 trapezoid sections, and then 2 placed on either side of the central hexagon. If we look at this image from RGV aerial, showing the inside of the staircase where all of these pipes are being routed to, we can see a control box used to collect and monitor the readout from these sensors.
We believe the goal of measuring the pressure in each of these zones is to make sure that there are no areas within the plates where the pressure is lower than expected at the time of ignition. The last thing SpaceX would want is for there to be a low pressure zone in the shower head where the hot exhaust plume gases would be able to sneak in through the holes. If the values were lower than expected, a possible solution could involve reducing the number of holes in the low pressure area or increasing the amount of head pressure in the water tanks.
After this test was completed, all of these pipes were removed, so it seems like SpaceX was satisfied with the data they gathered. When this system is not in use, it's important to make sure that it's kept clean in order to prevent dirt and debris from entering through the holes in the plate. So, in order to protect the shower head during these times, a pattern of thin steel plates are used to completely cover the top of the structure. You can see these cover plates pretty clearly in this overhead view from RGV aerial photography.
Wow. Honestly, that was a massive amount of information, even by my standards. But it's finally time to analyze the 33-engine static fire test performed on August 6. This is the culmination of everything we have learned here today.
Let's start off by examining the differences between the full pressure test of the system and the first few seconds of system initiation prior to ignition of the Raptor engines. When we compare these side by side, you can see that, once again, there was a very noticeable difference in the spray pattern from the shower head. In the full pressure test, we can see that the flow from the center plate, which is directed at a 30-degree angle, instantly overpowers the flow from the outer zones, which are spraying out at roughly 60-degree angle. This prevents the water from contacting the bottom of the launch mount. But during the static fire test, it seems like the pressure of water in the outer zones was significantly higher, which allowed it to overcome the water jets in the center and actually collide with the bottom of the deck. This change is probably a result of the data that they collected during the full pressure test of the system using those 8 sensors that I mentioned earlier. Now let's see how long it took for ignition to occur after the bleed valves on the weir pipe were closed. It appears that my guess was slightly off, and it actually took about 3 seconds for engine startup to begin after the start of the maximum flow rate period. I believe this was also a result of the data that they collected using those pressure sensors. The timing between these events may suggest that it takes 3 seconds for the system to reach the desired flow rate after the valve is closed. So, did this super heavy booster bidet system actually perform its job as expected? Well, when we look at the side-by-side comparisons showing the exhaust plume, you can really see the effect that the new active flame deflector is having. The most noticeable difference is that there is virtually no flames extending out from under the launch mount, whereas before, the flames were visible clear on the other side of the integration tower. This is even more noticeable in the overhead view from SpaceX, where you can see that the flames are essentially being contained within the footprint of the shower head and do not extend very far beyond that. The overall level of visibility is much greater as well. Comparing that to the integrated flight test, without the deluge system, it becomes nearly impossible to see the launch mount after the engines are ignited. Another obvious difference is the color of the exhaust plume. Looking at the side-by-side view again, we can see that with the upside-down shower head running, the plume is clearly consisting of mostly white steam instead of a huge cloud of brown dust and vaporized concrete. It also sticks much closer to the ground and barely rises above the height of the top of the booster. Previously, the plume ended up rising a few hundred meters above the top of the integration tower. I would say it's about 3 to 4 times higher than it is with the deluge system running. Next, let's look at the outward velocity of the plume. With the expansion of water turning into steam, and the effect of the water jets forcing everything out from the center of the blast surface, it appears that the plume expands out from the launch mount with much greater speed. I would say that this is a good sign that the system is doing a great job of accelerating the superheated exhaust gases outwards and preventing recirculation in the center of the blast surface.
During this test, we know that after ignition, there were 4 Raptor engines that shut down. Assuming all 33 engines were initially running, this would have meant that the booster was down to 29 engines. This is 1 less engine than during the integrated flight test. Due to the fact that this was intended to be a flight-like simulation of the booster, losing more than 3 should immediately trigger an abort, as would happen during a launch attempt.
According to the callouts heard during the SpaceX livestream, this was supposed to be a 5-second static fire, but was cut short after 2.74 seconds. The interesting thing about this is that as soon as the abort was triggered, we also noticed the depressor valves in the water tanks open up simultaneously. We will have to see another longer duration static fire test in order to say this for sure, but it seems like there may be some conditional programming in place to ensure that if an abort command is sent to the booster, it is also sent to the deluge control system as well. If true, this should help to conserve water and reduce the amount that has to be replaced during the recycle. But with that said, it still takes a long time for the water to stop flowing after the initiation of the depress. Given how early this system is activated before ignition, if there is a hold called within the last 5 seconds of the countdown, this will essentially result in a launch abort because there will no longer be enough water to proceed. So if that happens during the next launch attempt, you can pretty much guarantee that a detank will be announced shortly after. Once the water is on, the only option is to commit to launch or recycle and try again in 2 days. It will take at least a full day to refill the water tanks. In the future, we may expect to see a desalination plant installed somewhere at the launch complex, which could drastically improve on the recycle time. But for now, it's going to be done 4 trucks at a time. Overall, I would say that SpaceX was probably happy with the results of this test, minus the performance of the Raptor engines.
We reached a test duration of 2.74 seconds with 4 engines shutting down prematurely.
We weren't able to really see the condition of the top of the steel plates from the view of the drone camera once the test was over, but it seems like everything held up as expected. It was really awesome to see the fact that most of the paint on the launch mount was still in decent condition this time around. This is how it looked after the 33 engine test with water deluge versus the same test without this system installed. This is a massive difference. Even more impressive is the fact that in this shot from Starship Gazer, you can see that the engine cameras on the legs of the launch mount actually managed to survive this brutal static fire test. This is something we have never seen before. And on that note, sure would be nice if SpaceX would share those views one time so we could see what it looks like during ignition. We should expect to see at least one more static fire once Booster 9 returns to the launch site with its final upgrades. But don't forget, the true test will happen on launch day. We need to see a way higher thrust output from the booster before we can begin calling out all the naysayers. But if you ask me, I think it's going to do exactly what they're expecting it will.
I want to say a huge congratulations to the SpaceX team for pulling this off in such a short amount of time, though. The amount of work that went into this is simply incredible.
The very last question we're going to answer before wrapping this episode up is what happens to all the treated drinking water that is expelled during these tests? Well, after the initial test of this system, SpaceX did install a retention pond on the south side of the launch mount. Unfortunately, as it currently stands, I'm not really sure how effective this is. As you can tell, only a small fraction of the water actually makes its way into the retention pond. This is partially due to the fact that most of it completely overshoots the boundary of the pad and ends up in the wetlands. I don't think there's really anything that can be done about that currently. SpaceX originally planned to have a much larger retention pond, which would be located in this splash zone. I would expect that in the near future they may begin the process of getting the required Army Corps of Engineer approval or whatever else is needed in order to begin construction on that. If I had to guess, that might happen around the same time they get approval to construct the second orbital launch pad at this location. But we will see.
All right, everyone. I hope you all enjoyed this deep dive investigation. According to YouTube, 70% of folks who viewed the last deep dive are not subscribed to the channel. So if you learned something that you didn't know before today, then do us a favor and hit that subscribe button, and don't forget to leave a like as well. It really helps us out. I'm happy to announce that we have expanded the CSI Starbase merch store to include these Stage 0 t-shirts, which are available in several different color combinations. You can also get these CSI Starbase coffee mugs as well. You can find a link to our merchandise store in the description below. We greatly appreciate your support. All proceeds from these sales go into helping us purchase new equipment to increase the quality of these episodes. I want to thank all of our YouTube channel members and monthly supporters on Patreon, because we seriously could not do this without your support. On that note, I want to let you all know that I will be returning to work soon because it's very difficult to do this full time without creating a ton of financial stress. But don't worry, we will still continue to put out these deep dive investigations. They're just going to take a little longer for us to produce. Before we go, I want to say a huge thank you to Ryan Hansen Space for the ridiculous amount of work that went into modeling this system over the past few months. We had a lot of crucial help from the CSI Starbase team of investigators as well, but I think it's safe to say that there will be a lot of unanswered questions without his efforts. Make sure to support him on Patreon if you appreciate his work. I also want to give a huge shout out to Benedict 3D and the Virtual Space 3D team for the fantastic animations they created for this episode. You can find the links to support them as well in the description below. Of course, none of this would be possible without the footage from RGV Aerial Photography, Starship Gazer, Everyday Astronaut and the Cosmic Perspective team, and also the 24/7 live streams from Lab Padre and NASA Spaceflight. So thank you for all the incredible work you do to document the Starship program over the last few years. With that said, it's time for me to get out of here and spend some time back home in Colorado for a while. I hope to see you all in the next deep dive investigation. For now, this is Stage 0 Zach, signing off.